Okay guys, so here you can find now module 8 about the semantics of predicate logic, but first I would like to open the previous module. Let me just talk a bit about it and then to switch to the new module. Let me first close these tabs here. Oh jeez. Okay. What? This is not I wanted to open. Okay, so this is it, and I would like to emphasize that I ask you to read this module by yourself and try to learn it, because this is not this is a topic which we are going to learn more about in our exercise class. So in our exercise class tomorrow, we are going to solve exercises regarding this topic. First of all, we are going to learn how to formalize English sentences in predicate logic. In the module, there are a few examples. For example, here I have very short English sentences like this one or that one, and the last two sentences are the most interesting ones because they contain this word every, which is represented by this so-called quantifier. So we really need to learn how to formalize English sentences like those in the language of logic. Actually, uh, welcome to the second half of the semester, because predicate logic is the topic for the second half of the semester. The first half of the semester was dedicated to propositional logic. Well, in propositional logic, you couldn't even formalize sentences like this because it would be completely impossible. If you really need to talk about objects like humans or sweets or cars or I don't know, countries or any kind of objects, propositional logic is not sufficient. You really need to have such elements in your language, quantifiers and also variables like this x, where x can represent any object. So this is radically different from propositional logic. In propositional logic, variables can have only true or false values. In predicate logic, variables can have objects as values. This is a very huge jump, very huge step, actually, in formalization. Okay, what else do we need? Well, we definitely need so-called predicates. Age is a predicate, or L is a predicate, for example. These are actually functions which return true or false values. Like here, x likes y. X and y are two different objects, or maybe they are the same. This is also possible. And L, the predicate L, checks if this fact really holds or it does not. Once you have predicates, you can parameterize them. You can use the well-known logical connectives like conjunction, implication, whatever you learned before, you can use it here. Plus, as I already mentioned, you can use quantifiers. Quantifiers are really important and very strong operators in predicate logic. So this is the idea. This is what we are going to practice in the exercise class. In the exercise class, I will give you several English sentences. First, your task will be to choose variables, constants, predicates, whatever you need for formalizing those sentences. Okay, so this is something we will practice in our exercise class as well. Meanwhile, if you have any question, please don't hesitate to ask.
So the first half of the semester ends at the module number 6, right?
Yes, exactly.
No.
Exactly.
Okay.
From module number 1 to module number 6. So this is about propositional logic, and from now on we are going to talk about predicate logic. Actually, predicate logic is so powerful, so expressive, that at the end of this semester we are going to learn about a programming language. I might have already mentioned this. We are going to learn about the Prolog programming language, which is based on predicate logic. This is really crazy. So since I want you to learn about this programming language, you really need first to understand what is the syntax of predicate logic. So this is what module 7 is about. Then you need to understand what is the semantics of predicate logic. This is what module 8 is about. And after that, we are going to learn how to apply a resolution. Okay, so resolution to predicate logic. I hope you remember resolution is an algorithm, an automatic algorithm which can check our formulas, and you can prove, for example, that a formula is a logical law, or you can check logical consequence between formulas. And we learned how to use resolution for propositional logic. Soon we are going to learn how to use it for predicate logic, which will be, well, much more, not much more, but it will be a little bit more difficult. And after we learned how to use resolution predicate logic, then we will be able to learn about this Prolog programming language, because it uses resolution in the background. So I hope you will find this journey interesting. No other questions? Okay, besides understanding the meaning of the predicate logic, unfortunately, you must learn the basic concepts of first order or predicate logic. In module 7, in this section here, you can find the basic concepts and also their definitions. So this is something you also have to learn. First of all, the very fundamental concept is something which we call first order language, which consists of 3 sets actually. Okay, first of all, in the first half of the semester in propositional logic, before you started to formalize sentences, you learn that first Boolean variables are to be introduced. So for example, if you want to formalize sentences about cars, you have to first you have to introduce Boolean variables, true and false variables, which represent statements over cars. So for propositional logic, it was really easy to choose a language for your formulas. In first-order language, this is more difficult, more complex, because now you need variables to represent objects, right? Then you need predicates, these true and false valued functions over objects. And you might need also functions. Here in this section, I give you a few examples for first order language, but in our exercise class, this is exactly what we are going to do. First, we will choose a first order language, and then we will formalize sentences. Okay, then after you chose a first order language, then you will be able to construct formulas. So we really need to define what a formula looks like in predicate logic. Here is the definition. So this part of the definition might seem familiar to you, because this is exactly the same what we used for propositional logic. For example, here it is written how to use conjunction or implication or XOR and so on. But there are certain differences as well, very important differences compared to propositional logic. First of all, the most atomic element of formulas are called atoms, which look like this. So basically, we use a predicate and we parameterize it. You remember, predicate is a Boolean function, so it returns true or false for parameters. These are the parameters we pass to the predicate, t1, t2, tn. Here it is written that all of those are so-called terms. So this is something we have to understand what a term is. But first, let's check out this very last item here in the definition. Well, this is of course about quantifiers. You can use two types of quantifiers: universal quantifier or existential quantifier. I already mentioned they are about about iterating over the objects. You can say for all objects a statement is true, so this is what the universal quantifier is about. Or you can say there exists an object such that this statement is true. This is what you can use existential quantifiers for. So I hope you understand what are the differences here compared to propositional logic.
Yeah.
Okay, great. By the way, I have not corrected the error you found in module 7 yet, Oleg.
Oh yeah, and the same error is for the any too, not only for all. So
Oh.
no, it's not for 6. It's
Sorry, this is the same module. So where is it? Introducing quantifiers, probably.
It's in quantifiers in programming. And syntax and semantics. Now, in syntax.
Okay. Yeah. So already in module 7, we had something to learn about semantics. And here, okay. So here is the error you found.
Yeah, and
the same here, right?
And the next one.
Okay. Okay, I will correct it after we finished with this lecture. Thank you for noticing this error.
You're welcome.
It means we have the same error in the Hungarian version of this module. So I will correct those modules as well. Okay. Finally, the last definition I would like to mention in this module is the definition of a term, which you also have to learn for the exam. So yeah, I'm not going to explain this in details, but here you can find some explanation and exercises as well, I guess. And we are going to practice how to construct term in the exercise class as well. Okay. So if you don't have any further questions regarding module 7, but if you do, I'm open to any questions. Then I would switch to module 8. Okay, and basically what I want to do now is just give a quick overview what it is about. Then I will finish the lecture and I let you read the very details. Okay, so the semantics of predicate logic, this is the topic here. Basically, we learn how we can evaluate formulas, how we can decide if a formula is true or false. This is the basic task here. It seems to be easy to evaluate a formula. So let's see such a formula. So for example, let's see an example. Okay, so for example, here I have no formulas here, sorry. Okay, look at this example. So here I have a formula, this one. And the task here is to decide if it is false or true. So why is it so difficult? Well, first of all, this formula uses quantifiers. For all x, we check if there exists a y such that this statement is true. Well, it depends on several things, right? So first of all, what kind of objects do we have here? It does really matter. So for evaluating formulas, we definitely need a so-called domain. The domain specifies the set of objects you can substitute into variables such as x and y. So this is something we really need for evaluating the formula. But this is not enough, because here I have a constant, for example, a, So I really need to know what is the value of that constant, right? Yeah, exactly. So I need to fix a value for that constant. This is what we call interpreting the constant. I pick, of course, a value from the domain and put it here. The same I can do for the constant b. For b, I pick 2, for example. This is just an example. Okay, what else do I need? Well, I also have functions here, g and h. So I do need to interpret them as well. For example, this is how I interpret the function g. Basically, I specify what does it calculate, or what does h calculate. This is what we call interpreting functions. And finally, last but not least, I do need to interpret predicates as well. Q is a predicate. So basically, I have to specify when this predicate, which is a Boolean function, returns true, and when does it return false. Here I give the interpretation of all the predicates I introduced in my first order language. Okay, after all those interpretations here, and only after that, I am able to evaluate formulas like this one or that one or any other formulas. So it does seem complicated. And this is explained in this module, how to do that, what is behind all of that. There are actually 4 sections. This third section gives the definitions of all those parts which we need to evaluate terms and formulas. Before that, we have another section about bound variables and parameters. So this is the first section you need to understand. This is kind of an easy section. It explains that in formulas like those, for example, this one here, variables occur, like x occurs 3 times. And those occurrences can be either bound or free. Bound means that this variable occurrence is inside the scope of a quantifier. For example, here we have for all x, and this is the scope of this quantifier. Therefore, this occurrence of x is bound by this quantifier, and the same holds for this guy here. If we check out the first example, well, in this case, the scope of this quantifier is only px. So only this occurrence is bound. The other occurrence here inside Q is not bound, unbound or free. It's not bound by a quantifier. So this first section is about clarifying what we call a bound variable and what we call a free variable. I think it's very nicely explained. For example, Gábor Kusper uses colors to represent which variable is bound by which quantifier. Okay, let me continue. So there is a subsection about free variables and so on. The most important subsection here is about parameters of formulas. Here you have to understand that if a formula like this one here has a free variable, if you check this out, here only z is bound, so the occurrence of z are bound, but we have x and y, and they are unbound, they are free. So what to do with free variable occurrences, or in other words, parameters of the formula? Well, we can substitute arbitrary terms into those parameters. So you can substitute anything into x, you can substitute anything into y. Here Gabor gives an example. For example, here I substitute 5 into x, 10 into y, and only after substituting parameters to concrete values, with concrete terms, you can evaluate the formula. Actually, I think Gabor explains this very well in this subsection. For example, he gives an analogy with programming. In programming, soon we are going to learn about methods. This is a C# method with under this name. This is a Boolean function, so basically this is a predicate which has two parameters, x and y. And you can substitute anything into those parameters when you use this method in your program. The same you can do when representing this function as a logical formula. Just look at this. In C#, the implementation is so lengthy, right? In logic, you can do this in one line. It's amazing. But here my point is that this formula has also those parameters, capital X and capital Y, and you can substitute anything into those variables. And the value of this formula does depend on the values you substitute into those parameters. I hope you have a kind of picture about this now, because this will be important later when you evaluate formulas. For evaluating a formula, first you need to interpret everything inside that formula. I already told you that you have to specify a domain for your objects, you have to interpret constants, you have to interpret predicates, you have to interpret functions. I showed you an example before. But in most of the cases, this is not enough for evaluating a formula. You also need to assign concrete values to the parameters of the formula. So here in this subsection, it is written how to do that. Basically, you take every parameter here and you assign a concrete value to each of them. Here, the value comes from the domain. Once you fix the interpretation and the parameter assignment, you are able to evaluate formulas and also terms inside formulas. So in this page, on this page, it is written how to do that. Actually, what you are seeing now, it's just a lightweight definitions. So these are not real definitions, not exact definitions, just lightweight, easy definitions, because I didn't want to overwhelm you with lots of definitions. I think these descriptions are sufficient for you to understand how to evaluate terms and formulas, and you will be able to understand these examples here. By the way, here you can also you can also solve certain exercises, and also here in this subsection, which I already showed you. Okay, so to summarize, all of this looks quite complicated, but they are not that complicated. If you read all the material and solve the exercises, I'm pretty sure you will be able to understand how to evaluate formulas. No questions?
No.
Okay, last but not least, finally, the last section is about semantical properties, which you already know, by the way. We already learned about what does it mean that a formula is tautology, or in other term, logical law. We learned what does it mean to be satisfiable or unsatisfiable, and we also learned about logical consequence in propositional logic. Of course, in predicate logic, those concepts, those properties are a little bit more complicated, but not that complicated. Let me show you definitions. Like here, you can find the definition of a tautology or logical law. Okay, let's see. A formula is a tautology if for all interpretations and parameter assignments the formula is true. So it means the formula is always true. The details, which are now different from propositional logic, are represented by this short section of the sentence. Now interpretations are much more complicated inside, as I already showed you, and we also have parameter assignments. But the point is the same. And the point is the same for unsatisfiability. Here I will ask you to try to give here the correct answer, 0 or 1. You have to type it. And you will able to define what does it mean that a formula is satisfiable. Okay, so try to solve those exercises. You will be the ones who construct those two definitions. It's a huge responsibility. In a similar way, logical consequence looks quite the same as it looked in propositional logic. Of course, here again, interpretations are much more complicated, and we also have to deal with parameter assignments, but actually the point is the same. Whenever all the premises are true, the conclusion must be true. And at the end of the module, you will find two examples where I prove logical consequence, which seems, how to say, if I tell you that I have two such premises and this is the conclusion I want to prove. Do you have any question, Oleg? Because I can hear you.
Oh, no, sorry.
Okay. So it seems not that trivial how to do that. So here I give you a very short and easy derivation of proving that, yeah, this is a logical consequence of those two premises. It's not that complicated. Therefore, I give you another example at the very end, where I use, I don't know if you know this movie, it's an old movie, Monty Python and the Holy Grail. And in this movie, there is a funny scene where it is proven that this lady here is a witch. Does any of you know this movie?
No.
No. Okay, then just look at the scene. There are English subtitles as well. Okay, anyway, in this movie, this guy gives a gives a lot of statements, 6 to be exact. And if you look at them, they do use quantifiers. Actually, there is one statement which uses 2 quantifiers. Of course, there are predicates, several predicates. They are explained here. And yeah, so it is proven in the scene that from these premises, this conclusion can be derived. This means that the lady is a witch. Here I show you how to derive that this is true. Actually, it's not that trivial. Actually, I mean, it's easy to understand, but if I would tell you to give such a derivation, it's not that trivial. It was not that trivial for me as well, but it can be done. And yeah, and basically this is it. So just check out this example. I think it's fun, and it will give you an insight how we could prove, for example, that a formula is tautology or satisfiable, or we have logical consequence. Is not that trivial if we try to do this in this way. This is why we are going to recall resolution. You know, resolution is an algorithm which is kind of automated. We don't have to think too much. Here we do have to think how to proceed. But if we had an automated algorithm for proving any of those semantical properties, it would be so great. And actually, as we are going to learn, we will have such an algorithm. Resolution, it is called resolution. Of course, for resolution, there are several things we need to learn before, because I hope you remember resolution takes a CNF as input. So we first really need to learn how to convert formulas like those to CNF. Or let's start with this question: what a CNF looks like in predicate logic. It's not that straightforward, because now we have predicates and quantifiers and all those stuff. So this is what we are going to learn about next time: what CNF means in predicate logic and how to translate formulas to CNF. It will be not that easy, but you will understand that as well. Okay, guys, that's it. You still have a chance to ask questions or give me any feedback.
Will there be a PowerPoint for module 7 and 8?
Sorry, the sound was quite bad. Could you repeat your question, please?
Will we have a PowerPoint for module 7 and module 8?
Okay, PowerPoint. Yeah, I have a PowerPoint presentation for module 7. I will upload it in a few minutes. Unfortunately, I don't have any PowerPoint presentation for module 8. Or I have one. Let me show this to you. So I typically show this PowerPoint presentation for module 8. This is it.
Yeah.
Because I typically ask the students to to learn this module by themselves, because frankly to say, this topic, the semantics of predicate logic, is not that important than the other topics about predicate logic. For example, the previous module was much more important, module 7.
But it's like a brick, like a tower. You have to build it. If the base is not right, so the whole building will fall down.
Yeah,
I think I will search for predicate logic examples straightforward without going into the introduction. So like to go into the exercise itself, so I can know more about the symbols and all of this.
Okay, great, really great, good idea. We will also, as I already mentioned, we will also I will also give you examples in the exercise class, a lot of examples.
Okay.
Okay, guys, thank you for attending the lecture. So please read the module, solve the exercises, and see you tomorrow in the exercise class.
See you.
See you. Bye bye.
See you.